So, how can scientists tell if a population has evolving, like right now, just by looking at its genes? Well, it turns out there's a surprisingly simple mathematical baseline they use to spot change as it's happening. Let's dive in and see how it works. Okay, imagine this. You are standing in front of this huge, beautiful field of wildflowers. You've got pink ones, you've got white ones. Now, if you came back, let's say in 50 years, what do you think you would see? Would it be the same exact mix of colors, or would one color maybe start to take over? This is the kind of core question that Hardy-Weinberg Principle really help us tackle. So, to measure any kind of a change, you need a starting point, right? A baseline where nothing is changing. And that's exactly what the Hardy-Weinberg Principle is. It's this perfect theoretic world, a snapshot where a population is totally stable, kind of frozen in time and not evolving one bit. And this state of perfect, unchanging stability. We call that equilibrium. It's a completely hypothetical situation where the genetic makeup of the population is just locked in, generation after generation. The ratio of those pink flower to white flower genes would stay exactly the same, no changes allowed. Okay, so for a population to actually hit this perfect hypothetical equilibrium, it has to follow 5 super strict rules seriously. Think of it like a recipe for putting a complete stop to evolution. First up, no new genes are allowed. That means 0 mutations. Second, mating has to be totally random. No picking and choosing. Third, no one can come in or leave the population, so no gene flu. Fourth, the population has to be huge. We are talking massive, so that random luck cannot mess with the members. And finally, number 5, everybody has to have the exact same chance of surviving and having kids, so absolutely no natural selection. Now, does that sound like any real population on Earth? Yeah, probably not. And believe it or not, that's the whole point. So, how do we actually track this perfect ideal world with a little bit of algebra? But don't worry, don't let the word math scare you off. It's not complicated stuff, it's much more like simple bookkeeping for all the genes floating around in a population. Okay, first things first, we need to know what we are actually counting. And the basic unit here is the allele. An allele is just a specific version of a gene. So, for our wildflowers, we had one allele for pink petals and another allele for white petals. Simple as that, alright? This first equation is super simple. It just tracks all the alleles in the gene pool. We use the letter P for the frequency of the dominant allele and Q for the recessive one. And since those are the only 2 options, if you add them together, P plus Q, they have to equals 1, which just stands for a 100% of all the alleles out there. Okay, so now we are gonna zoom in from that big picture gene pool to the individual flowers themselves. We need to look at their genotype, and the genotype is just the specific pair of alleles that an individual organism is carrying around. And this next equation lets us predict how many of each genotype we should find in the population. You know, each combination of alleles now, I know it looks a little more complex, but trust me, it's really just built on the simple probability of pulling those P and Q alleles out of the gene pool we just talked about. So let's break this down really quick. P square, that's the percentage of the population with 2 dominant alleles. Q square, that's the folks with 2 recessive alleles. And that, the middle part, 2PQ, that's the really useful one. It tells us how many heterozygotes there are, the individuals carrying one of each allele. And just like before, if you add them all up, you get 1 or 100% of the population. Okay, so we have got our perfect model. We got our neat and tidy equations. But what happens when we step out into the messy real world and we start counting the actual flowers or animals or people, and the numbers just don't fit our perfect prediction? And this right, here's where the Hardy-Weinberg Principle becomes so incredibly powerful. So, what does it mean when real life doesn't match the math? When reality breaks away from the perfect baseline we calculated? So let's say our equation predicts that only 4% of the wildflowers should be white. That's our homozygous recessive group. But then we go out to the field, we do the hard work of counting, and we find that 50% of them are white. That massive difference, that's a giant red flag for a biologist. And here's the absolute key takeaway. When the calculation fails, it's not a mistake, it's a discovery. It's mathematical proof that one of those 5 perfect world rules has been broken. It's evidence that the population is in fact actively evolving. So the model's failure is actually its greatest success, and this way more than just some abstract tool for studying flowers in a field. This principle has real, profound, and sometimes even life-saving applications in human medicine. I mean, this is not just theory. Genetic counselors use this exact principle all the time. It allows them to estimate how many people in a population are silent carriers of a genetic disease, even if they seem perfectly healthy and have no symptoms at all. Let's take a real-world example. Imagine there is a recessive genetic disorder that shows up in about 1 in every 2,500 births. That number, that one we can actually see and count. That's our Q-square value. It's the frequency of people who have 2 copies of that recessive allele, and here is where the magic happens. We can't take that one number we can actually see Q square and work backward. We take the square root of it. So that you have got Q, and since we know P plus Q equals 1, it's super easy to figure out P. And once you have both P and Q, you can calculate 2PQ and find the hidden number of the carriers in that population. It's just a brilliant illustration of how powerful this is. Start with one little clue. You can see the number of people with the disease, and you can solve a much bigger mystery. How many people are slightly carrying the gene? Ultimately, the Hardy-Weinberg Principle was a game changer. It helped turn biology from a science that just described what it saw into one that could actually make predictions. It gives us that perfect baseline, that what if nothing changed scenario, so that when we see where reality breaks from that baseline, we can pinpoint exactly where and how life is evolving. So, at the end of the day, the logic is really simple. If your real-world numbers match the equation, the population is stable. If the number doesn't match, you have just found evidence that evolution is happening. It's like the math itself becomes the control group in the grand experiment of life. So the next time you are out and you see a group of animals or plants or even just people, ask yourself what evolutionary forces might be acting on them right now. What pressure could be pushing their genetics away from the perfect and changing equilibrium? Something to think about. Thanks for tuning in.